volumes by cylindrical shells. So let's look at a region R. We're looking from A to B and we have this function. And what if we rotate this function around the y-axis? We can visualize the solid that would be generated if we rotated this around the y-axis, and it would have this cylindrical hole in the middle and kind of have this bell shape. Now if we were interested in finding the volume of this, we're going to have a second method called the shell method. For this function we're going to pick a little representative x when we're rotating around the y-axis, and so we look at this rectangle here with x bar sub k in that rectangle, and then we're going to rotate this region around the y-axis, and let's watch what this little rectangle does as we rotate this around. Now as you can see this rectangle moving around, we can start to see what this is generating, both the complete solid and what this rectangle is doing. And so as we continue on around the y-axis here, and then we see that we're starting to form this as we continue the rest of the way, we see that we form this shell. What it is, it looks like a cylinder, but it has a little thickness to it as well, and we could look at it at any x. We just picked a representative x, and they would all have these shells, but they would have different radii depending on what x you picked. And if we could take each of these shells then at all of these different spots, and we could sum up the volumes of each of these shells, we would have an approximate for the volume of this solid generated. So that's the idea behind the shell method. So let's look at it a little bit closer. So here is our region, and we're going to look at some representative rectangle. It's going to have our little thickness delta x, and we're going to pick an x on that interval that forms this rectangle, so we're calling that x bar sub k. And then if we wanted to know the height of that rectangle, that's going to just be our function value at x bar sub k. So as we think about rotating this around and seeing what this rectangle does, it forms this shell. And so if we want to find the volume of this cylindrical shell, we see that it has our little thickness delta x. And as we kind of try and picture what that would look like, then our radius is going to be x bar sub k, and then our height is going to be our function value at x bar sub k, and our thickness is going to be delta x. Now let's take the shell and let's cut it open and kind of spread it out, and you can see what you get is a rectangle, but then we have this little thickness delta x. Think of maybe like a soup label or something that's wrapped around a cylinder, and if you cut it and undo it here, this is what it looks like. So the height of this is going to be our function value at our representative x, and the thickness is going to be our little delta x. And then the length of this, well, this was wrapped around and formed this circle, and so the length around that is going to be the circumference of the circle, which is 2 pi r, and our r in this case is our representative x, x bar sub k. So the length here is going to be that circumference, which is 2 pi r, or 2 pi x bar sub k. So we could find this volume then by just simply timesing length times width times height, or in this case we've got height and length and thickness. And then we could sum all of these up to get an approximate for the volume. So we have our 2 pi r, which is x bar sub k, that's our circumference or our length, multiplied by the height, f of x bar sub k, multiplied by the width, in this case our little thickness delta x. I'm sure you can see where we're going with this. We're going to then take the limit as the number of these rectangles, or these cylindrical shells, the little rectangles that get rotated around form the cylindrical shells, goes to infinity. So we simply just have each of these pieces, which is just length times width times height, and in the limit we have then the integral from a to b of 2 pi x, that's our circumference, our length, multiplied by the height, f of x, multiplied by our width, our little thickness, dx. as we took this and we increased the number of shells and let n approach infinity, then when we get the integral, we have the exact volume. Now let's see what would happen if we had a region that was bounded above by a function, we'll call it f of x, and below by another function, g of x. So it's not going down to the x-axis. We're going to rotate around the y, see what a little rectangle does as we do this one. So the difference here is we are not using the x-axis as one of our boundaries of our region. Let's watch that little rectangle then, and let's rotate this around, and we can see that that rectangle is again generating a cylindrical shell, but the important thing to see here is that shell does not extend down to the x-axis, and so the height of that shell is not the function value because there are two functions here. So as we look around, we still see we have this radius, that's going to be 2 pi and our representative x wherever we are. But as we look to see this height of the shell, it's going to be the upper function minus the lower function. If we take the difference between those and take out this other missing piece here by subtracting those two functions, we will have the height of this shell. We can put those shells in various places there, then we could sum all of those up and we would have the volume of this solid that is generated. So let's look at this just a little bit closer then and see if we can express this looking at one of those cylindrical shells. Then we know that the length, if we were looking at this and we had cut it open and spread it out, would be the circumference. So that would be 2 pi x bar sub k, some representative x wherever we are there. And the height would be the upper function minus the lower function at that x bar sub k. So in our case, f of x bar sub k minus g of x bar sub k. And then the little width is our delta x. And then of course if we let n, the limit as n approaches infinity, we have the volume as an integral that will express the volume of this solid generated. So it is the integral from a to b of 2 pi x, and then our f of x minus g of x to give us our height times our little thickness dx. So here is kind of a summary of the shell method, and this works for all functions, including if we happen to go down to the x-axis, then our g function is just 0. So this formula works for either case. So let f and g be continuous functions with f of x greater than or equal to g of x on this closed interval from a to b. If R is the region bounded by the curves y equal f of x and y equal g of x between the lines x equal a and x equal b, the volume of the solid generated when R is revolved around the y-axis is given here. The integral from a to b, 2 pi x times quantity f of x minus g of x times dx. Again, rather than memorize a formula though, if you will make a quick sketch so you can visualize what's going on and think of this in terms of taking that shell and multiplying length times width times height, and our length is going to be our circumference around, and then our width is our delta x or delta y depending on which axis we're rotating around. This one is explaining around the y-axis. We could do analogous things around the x-axis, sum all of those up, and we have the volume. So now that we have two methods, and we'll see some examples of the shell method following this video, but now that we have two methods, which method should you use? Well, we actually have disk, washer, and shell, but really disk is a special case of washer because you could use the washer method and have that other function be 0. So when we had f minus g, if g was 0, then it's essentially the disk method. So we really have two methods, the washer method and the shell method. Which one should you use? And in principle, you should be able to use either one. You could say, I'm going to sum this up with slices and looking at washers, or I'm going to look at cylindrical shells and sum those up. However, in practice, one of them usually produces an easier integral to evaluate than the other. And so if you set one up and it looks like something you don't know how to integrate or going to be tough to integrate, then you may want to try the other method and see what kind of an integral you get. So let's just summarize these. And again, it's important to not try and just memorize formulas, but draw a picture and look at it to see what you've got. So first of all, we're going to look at the disk method or washer method about the x-axis. So if we're rotating around the x-axis, we have these little disks generated, and our little representative slice will be a little thickness dx here. And then we're looking at the picture and we see we have a big radius and then minus the radius of the hole. So we would be integrating here from A to B, and if we find the area of the disk, that's going to be pi times the y value, or the upper function f of x squared, minus, and we're going to subtract off this hole, that's going to be pi g of x squared, and then multiplied by our little thickness dx. So here is our integral. This is just what we said, but you could factor out a pi. Now, if another integration with respect to x is if we are rotating around the y-axis and we are doing the shell method. And we know it's with respect to x because as we look at our little representative slice or rectangle, that's a little thickness again, dx. Now as we do that, then as we're looking here, we essentially want to figure out this piece that has our little thickness here as it was spread out, and so we know this length is going to be 2 pi, and we can see that's going to be the x value here for the r. And then we see our height is going to be this upper function minus this lower function, and then we got our little thickness dx. So here's our circumference, 2 pi x. Here is our height, f of x minus g of x, and our little thickness dx. Now, integrations with respect to y, if we're using the disk washer method and we're rotating around the y-axis, then we can see that the disks or washers here are perpendicular to the y-axis, and as we look at our representative slice, we see it has a little thickness dy. So that lets us know we want the functions expressed in terms of y, and we will be integrating with respect to y. So as I express this, as I look at the area of the big disk, well, that's pi, and then this x value here, which is p of y squared, and then subtract off the area of the hole, well, that's pi, and then here's our q of y squared, and then multiply by our little thickness dy. And we were integrating here from c to d. And finally, another integration with respect to y is if we were rotating around the x-axis but using the shell method. So these little shells would go parallel to the x-axis, and you can see that that has a little thickness dy. And as I go to express this, again, I would think of this spread out, and this would be my circumference. So if I'm trying to get my circumference here, it's going to be 2 pi r, and we can see that r is going to be our y value. So that's going to be 2 pi y. And then we need to multiply it by this height here, and that height here is going to be this function p of y minus this function q of y. And then we'd need to multiply by our little thickness dy, and then we would integrate that from c to d. So looking at the picture and understanding what each of the methods is should have us come up with this formula.